Section 3 is completely about standing waves. Now we are going to learn how to make sound by an instrument. First, standing waves on a vibrating string generates the sound. Now watch this movie. Slow motion. These strings, vibrating strings, they are vibrating with some standing waves, and then they generate sound. This is all. Sound is generated by standing waves. First thing you should know that. Standing waves are formed, you know that, at certain frequencies and then certain wavelengths. That's why frequency of the sound produced by a string is equal to frequency of the standing wave formed on the string. There are standing waves formed on the string at certain frequencies, at certain wavelengths, and sounds appearing from this string is going to be the same frequency of the standing wave formed in a string. So just I'm going to remind you standing waves. Remember, you can vibrate a string at different wavelengths, at specific wavelengths, so at different modes. So the first one is this one. It was first order standing wave. It was only one loop. And because ends are fixed, this is fixed, that is fixed. So fixed ends are not vibrating, and they were called notes. But the point between the two notes are vibrating with the largest amplitude. So this point was said antinote. This is the first order standing wave. But if you increase the frequency of the vibration, in this case, you are going to observe second order standing wave with two loops. Again, ends are fixed, they are notes, but this time there will be two loops. So one loop is going to be here, other loop is going to be right there. And again, this point is also not vibrating, it's also note. Between two notes, always there is antinote, a point with the largest amplitude, vibrating with largest amplitude. This is two loops. This standing wave or second order standing wave contains two loops. And we said that number of loops and number of antinodes are equal. Two loops, two antinodes, one loop, one antinode. But number of notes is one greater than number of antinodes. Here is 1, 2, 3 notes for a string or string fixed at both ends. Okay, these were the possible standing waves which could happen on a string that is fixed at both ends. Length of the standing wave is, length of the string is L. First order, second order, third order, fourth order. It goes on like this. If you are able to increase the frequency, so you can get fifth, sixth, seventh, so if you are able to do that. And we knew that the distance between two successive notes and two successive antinodes is half of a wavelength. Yani that distance, this is one note, another note. This separation between note to note, successive, means one after another. Lambda over 2. This is note. This is another note. This is one more note. So again, separation between them is lambda over 2. This is lambda over 2. That is also lambda over 2. Or note, 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 note. There are 1, 2, 3, 4 notes. Again, separation between notes are lambda over 2. But as frequency increases from first to third, wavelength decreases. As you see, notes are approaching each other. Wavelength decreases. This makes sense because according to the equation of the speed, lambda times f, if frequency increases, lambda must decrease to keep speed of the wave in this string is constant. This is logical. So again, this is the fourth one. So note, 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 note. So then again, separation between the notes are lambda over 2. Also, separation between antinodes are lambda over 2, half of the wavelength. And then, as I said, standing waves are formed at specific frequencies at some specific wavelength, not at every frequency, not at every wavelength. And I gave an equation. This equation is saying you at what wavelength you can produce a standing wave. For example, the first order n is equal to 1. You will write here 1. So in first order, you can produce a standing wave whose wavelength is twice of the length, 2L, because when you are going to write here is 1 and 1. So the first order standing wave forms at a wavelength which is equal to 2 times of the length of the string. What about the second one? Second order n is equal to 2. So you are going to write here 2. You are going to write here 2. Lambda 2 for the second one. So lambda 2 is going to be exactly the same as the length of the string. Yani, so this is the lambda 2, which is going to be exactly the same length of the string. For third one, you are going to write here 2L over 3. For fourth one, 2L over 4. And it goes on like this. And you can get at what wavelength you can obtain standing wave on a string or on a rope or on a spring. All the difference right now we are going to do is that we are not going to represent the standing wave by wavelengths. We will represent them by frequency. How? Instead of lambda, I am going to write its equivalent. Go. What is it lambda equal from this equation? Lambda is equal to V divided by F. I will write here, instead of lambda, V divided by Fn is equal to 2L over N. So I will cross product it. Fn multiplied by 2L is going to be N times V divided by 2L divided by 2L. So you will get the frequency equation. Fn is going to be N multiplied by V divided by 2L. So you can also write the frequency equation. Yani at what frequency you can form a standing wave on a string. We are going to calculate with this equation in section 3 in the harmonics. Because of the string instruments, ends are fixed. Ends are fixed. It's a string instrument. Every string instrument ends are fixed. For that reason, both ends are going to be notes. Between the notes, there will be, of course, antinodes. So if this is the first order standing wave, it's going to be like this. So in here, it's going to be antinode. If it is second order standing wave like this, so it's going to be this way. So only difference, instead of standing waves, now we are going to say harmonics. These are harmonics. This is first harmonic. This is going to be second harmonic, third harmonic, fourth harmonic. It will go like this. Only we are, instead of saying first order standing wave, I am going to say right now first harmonic, second harmonic, third harmonic, fourth harmonic, and so on. As I said, the ends of the string which cannot vibrate will be note. And string experience the most displacement, yani greatest displacement between two notes, which is called antinode. We know about this. And we also know that distance from one note to another note is lambda over 2, half of a wavelength. Or distance from one antinode to another antinode is also lambda over 2. Those things are all we know. And this is the first harmonic. First harmonic, first order standing wave. So in first order standing wave, so then length of the string is going to be equal half of the wavelength. How do I know? Because separation between from node to another node is lambda over 2, yani 0.5 lambda So then if I make them equal, I can get the frequency of the first harmonic mathematically. 0.5 lambda 1 is equal to length of the string. So then 0.5 means 1 over 2. Lambda 1, how can I write lambda? V is equal to lambda times f. So then lambda is equal to V divided by f. So instead of lambda 1, I will write V divided by f1. V divided by fn is equal to L. So then I will get f1 in here, L right here. F1 is going to be V divided by 2L. So this is the frequency of the first harmonic. Yani at this frequency, first order standing wave, yani first harmonic, will form on this string. This is the smallest frequency. So this is the smallest frequency, the lowest possible frequency that can produce a standing wave in a string, which is known as fundamental frequency. If the frequency is the lowest, according to the equation of speed of a wave, lambda times f, if it is lowest, part of frequency is lowest, so wavelength must be longest, because v is constant. So that's why at the first harmonic, standing wave gets its longest possible wavelength. Longest possible wavelength will be in first order or the first harmonic or first order standing wave. And first order standing wave, as we know, or first harmonic, consists only one loop, one note, two antinodes. Second order standing wave or second harmonic will have two loops. So two loops, two antinodes, one antinode, second antinode. And we know that number of nodes is going to be 1 greater than number of antinodes. A second order standing wave or second harmonic is going to be a frequency which is twice of the first one. So you can prove it mathematically. Let's do it in here. I will make again. So from node to node, lambda over 2. One more lambda 2 in here. Lambda over 2, lambda over 2. When you add them, it becomes lambda. So distance, length of the string is equal to 1 wavelength. If lambda 2 is equal to 1 wavelength, instead of lambda 2, just write it. V over F2 is equal to L. So F2 is going to be V over L. So F2 is equal to V over L. What about F1? V over 2L. So as you see, you multiplied F1 by 2. If you multiply this by 2, you will get V over L. So that's why second harmonic will have a frequency twice of the first harmonic. And it goes on like this. Third harmonic will have a frequency 3 times of the first harmonic. So fourth harmonic will have a frequency 4 times of the first harmonic or fundamental frequency. So that's why harmonic series, these are called harmonic series, first, second, third, fourth, fifth, sixth. So these standing waves can form multiple number of the fundamental frequency. That's why your equation, just I in fact showed when I was explaining standing waves. So frequency equation for harmonic series in a vibrating string is going to be n multiplied by V divided by 2L, where n starts first harmonic, for second harmonic 2, for third harmonic 3, for fourth harmonic 4, for fifth harmonic 5, and so on. You can go on. So V over 2L is called fundamental frequency. So then if you multiply fundamental frequency with 2, you will get the frequency of the second harmonic. If you multiply fundamental frequency with 3, you will get the frequency of the third harmonic. With 4, frequency of the fourth harmonic, and so on. So n is going to be order of harmonics. Also, it represents number of loops or number of antinodes. And we know that number of nodes is going to be 1 greater than number of antinodes. According to the fundamental frequency equation, n is equal to V divided by 2L. Two factors determine the fundamental frequency. One of them is speed of the wave in the string. Second one is the length of the string. So you can change fundamental frequency by changing the speed of the wave in the string and by changing the length of the string. All musical instruments are working with this principle, making a different sound. Now watch, there's a movie about that.
On this board is a string which is fixed at one end and attached to some weights at the other. Listen to the sound the string makes when it's plucked. We can see that the string is vibrating to produce the sound. Now listen again after an extra weight is added.
So when he adds extra weight, what is he doing? He's increasing something, is it? He's changing property of the medium. So if you add more weights, you are going to increase the tension in the string. Remember, you can change the speed of a wave in a medium by two ways. One of them is you can change the medium type. Second one is you can change property of the medium. In here, he's adding more weights and he's increasing the tension in the string. So if you increase the tension, wave starts moving faster. So now if wave starts moving faster, you are going to hear a high frequency. Now watch.
The string now produces a sound with a higher pitch. The weights pull the string so it becomes tighter and so vibrates faster when it's plucked. There are other ways of affecting the sound pitch of a string.
One of them is this. So you can increase the tension in the string and then you can change the frequency of the sound. Follow again from the beginning.
On this board is a string which is fixed at one end and attached to some weights at the other. Listen to the sound the string makes when it's plucked. We can see that the string is vibrating to produce the sound. Now listen again after an extra weight is added. The string now produces a sound with a higher pitch. The weights pull the string so it becomes tighter and so vibrates faster when it's plucked. There are other ways of affecting
Second one is the length
of a string. These strings all have different lengths. The vibrating length of string is between the black strips of wood.
When it is shorter, frequency increases,
the weight
correct?
on each string is the same. The longer strings produce a lower pitch sound than the shorter strings.
Longer, middle, shorter. So it is normal because according to the equation,
vibrating faster than the longer lengths.
As length
all these strings are the same length and have the same weight attached. The difference this time is their thickness.
There are two problems, and in fact problems are not so hard. A violin string that is 50 centimeter long has a fundamental frequency of 440 hertz. What is the speed of the wave on the string? Question is that. Length of the string is given, so L is 50 centimeter, 0.5 meters. Fundamental frequency F1, fundamental frequency is 440 hertz. So what is the speed of the wave in the string? We know that fundamental frequency equation is V divided by 2L for string instruments. We are going to write the given into cross product. So V is going to be F1 multiplied by 2L. So to get the V, F1 is given as 440 hertz, 2L, 2 multiplied by 0.5. So you will get is 440 meters per second. And next one, the note middle C has a fundamental frequency F1, 262 hertz, fundamental frequency. What is the second harmonic? F2, frequency of the second harmonic. So we know that harmonic series goes like this, n multiplied by F1. For second harmonic, n is equal to 2. So F2 must be equal to 2 times of the fundamental frequency. So 2 times of fundamental frequency 262 it's going to be 524. This is the second harmonic. If the question was third harmonic, 3 times fundamental frequency. Fourth harmonic, 4 times fundamental frequency, so on. It will go so on. Question 2 says that if the wire is 66 centimeter long, length of the wire is given, 0.66 meters. What is the speed of the wave on the string? It's asking you. So, according to the fundamental frequency equation, use fundamental frequency equation. F1 is equal to V divided by 2L again. Cross product, you can get V as fundamental frequency multiplied by 2L. Fundamental frequency 262 multiplied by 2L, L is 0.66. When you multiply them all, you are going to get the speed 346 meters per second.